So changing topics. I'll talk about generally Quarkonium and Quark-Gluon plasma, and these are not words that have been mentioned too often in this workshop, so I'll spend a half to two-thirds of the talk discussing why this is an interesting problem, what's the experimental status on these words that I've just introduced, and then enumerate or mention a small research program that we've put together towards understanding Quarkonium transport in Quark-Gluon plasma. So let's begin with how do we even think about this problem at all? And for the past 20, maybe even 30 years or so, experimentalists have been doing heavy ion collisions. They've been colliding head-on to highly Lorentz contracted, say, lead nuclei, which impact right on each other. And a short time after that, you saw there was a red blob there, which in this cartoon you identify as the high temperature phase of QCD. And then eventually things cool off, stream away, fly off to the detectors in the accelerator that will be down here or up there. And all this happens in a really small time. If you see here, the time variable is like 90 Fermi over C, so 10 to the minus 21, 22 seconds. I might have gotten an order of magnitude wrong, but a very fast process that tells us about how many body dynamics of QCD takes place in real life. More of a cartoon, what you do is you take two lead or gold nuclei, which are the favorites for colliding. Don't ask me too much about why. They collide. They have a zone where they overlap. After that, there's some pre-equilibrium dynamics in which this system thermalizes, and then suddenly Quark-Gluon plasma appears. This collision, if it's a sufficiently high energy, lands at a temperature on the phase diagram that is above the crossover transition. And then after that, there's about 10 Fermi over C of time of basically hydrodynamic evolution of this plasma. Eventually it reaches the QCD crossover temperature, it starts to hadronize. Things are still in kinetic equilibrium until eventually you get to even lower temperatures of order like 100 MeV. And then you just get particles, pions, kaons, protons, neutrons, and they fly away over to our detector. This is qualitatively similar to what happens in the cosmology. You have a very high energy process at the earliest times. Then you have matter in thermal equilibrium. So as the universe expands, everything cools down. And then at some point, particles stop scattering. Everything freezes out. Then gravity does other things here. But then at the end of the day, we can see the imprints of what happened at early times at high temperatures with our telescopes, which are our detectors. So in a sense, in a mildly exaggerated way, you can say that you're reproducing the early universe here, because this phase of matter, the Quark-Gluon plasma, would have been present also here in the early universe when the temperature was high enough. Now, just because I've mentioned QCD, the phases of QCD a couple of times, let me review what the status is on the QCD phase diagram. So we know that at low temperatures and low chemical potentials, essentially we have a hadron gas. As we dial up the temperature to around 150 MeV, there's a crossover, and above that we see a Quark-Gluon plasma pretty much everywhere. To be fair, what is well understood from first principles lattice QCD calculations is somewhere from this line here to the left, because there's a notorious sign problem when we try to evaluate the path integrals at a finite baryon chemical potential. Down here you'd learn about presumably neutron stars, but since QCD is non-perturbative there, what people actually do is play the game the other way around. You look at neutron star observations, you constrain the equation of state down here from chiral perturbation theory and up there from perturbative QCD, and And from there, you get information into what's happening in this regime. For today, I'm going to be focusing mostly on the zero chemical potential line, well, entirely on the zero chemical potential line, and on these very high energy collisions that the LHC does, whose path in the phase diagram is laid out by this line. By the way, if you've been following the news, last week, the Beam Energy Scan 2 experiment, which had projected these curves a long time ago, finally released their experimental observations about whether they have found this critical point or not. The answer was sadly negative, or at least inconclusive. So the theory talks in that conference right after that conveniently moved the critical point to 600 MeV. And well, that's life. I mean, this is just the forecast of what you would have been able to measure if it had been there. But also, since you'll see that these lines here land like increasingly lower on the phase diagram, and if you kept lowering the collision energy, eventually you'd land down here because you're bound to collide nuclear matter. Those are the basic matter from which you start the collision. So eventually the time during which you're probing thermodynamics in a heavy ion collision gets much shorter in the quark-gluon plasma phase. So even here, there are many things that you have to think harder about out of equilibrium effects. And so I would say it's inconclusive, but if you look at the theory talks that came right after, you'd say they moved it to 600. Well, that's life.
So I've heard of BS, which is Beijing electron synchrotron. That's another BS?
That's another BS. This is the Beam Energy Scan 2 program at the Relativistic Heavy Ion Collider at Brookhaven.
At Brookhaven.
Yeah, the other one is, and they do different kind of.
Yeah, very different.
Was they who did last week? I think they. Well, anyways, let me not get carried away. Okay, so I hope I told you enough about quark-gluon plasma. Now, the other buzzword in my title was quarkonium, and there are two species of quarkonium that I'm going to be focusing on today. Well, mostly one of them actually. But you should have in mind termonium and botamonium, bound states of heavy quark and anti-quark pairs. So there's the famous J-psi particle, and here I've listed the masses from what you look up in the particle data group webpage, and well, they're what they are. The interesting thing, though, is that their masses are much higher than the scale fixed by lambda QCD. So you can hope to treat the dynamics of these heavy quarks and bound states in perturbation theory. And they're also interesting in the context of heavy ion collisions because their decay widths of these states go over much longer times than the typical lifetime of the quark-gluon plasma, which is 10 Fermi over C. So for the purposes of heavy ion collisions, these states are really long-lived. So you can ask questions about them and see how the quark-gluon plasma modifies their propagation and eventually see a confinement-deconfinement transition in these states induced by screening in the interaction between the heavy quarks. That was this was an old idea by Matsui and Satz in the 80s, I believe, which has been pursued in the heavy ion collision program ever since. And essentially what people do is look at suppression ratios of quarkonia and heavy quark and hadrons with heavy quarks relative to proton-proton collisions. And the idea is to use these states as kind of a thermometer of the quark-gluon plasma, because if the temperature would be high enough, you expect that the formation of bound states would be suppressed. And as such, well, you want to go and experiment, collide heavy ions and see what you get. This is what the most recent result, I believe, from the CMS collaboration. So this is a paper from last year. This tells you, so one would be if there were no medium modifications, so if there were just vacuum, so This represents the ratio between how many upsilons, so BB bar bound states, you find at the end of the day in your detector, or their decay products rather, but let's just talk about upsilons, relative to what you see in proton-proton collisions. So it's essentially telling you how much the quark-gluon plasma alters, or rather suppresses, the formation of these bound states. And you see that experimentalists have got...
N is...
Oh yeah, good. So there are two plots here. At the left, it's a function of how many nucleons collided with each other, so how central the collision was. And on the right is summed over all of these, but marginalized over the transverse momentum of the bound state that comes out. And this is what experimentalists can do nowadays. They can give us very good data with comparatively very small error bars. We can very definitely see that the formation of bound states is suppressed, and that this is sequential. The 1s is less suppressed than the 2s, which is less suppressed than the 3s. So, and 3s, these are analog notation this is analog notation for what the hydrogen energy level would be. So hydrogen energy levels would be. So they're like essentially bigger and bigger states, which would have more space to interact with the quark-gluon plasma. Now, that's experiment.
Why did the first one increase?
Oh, up here? That's because if you have a very very peripheral collision where you have essentially only one nucleon colliding with each other, you go back to the proton-proton baseline. So you expect to be up here at 1.
No, but why does it start at 0.8?
Ah, these. That's a very good question. Yeah, I mean, there's an error bar there. So that's statistically, you're not supposed to. If you have error bars, you're supposed to miss something. But I don't have something. I don't have something very good to say about why this is so up here. I mean, I could say more things, but I would get derailed in things that I don't want to. Things that are messier than this. Now, this is experiment. So the CMS collaboration was nice enough to not overlay theory curves here. Because if you do that, like the Alice collaboration did a few years ago, it looks much messier. So the theory error bars are larger than the experiment error bars. And by theory, I mean any model you write down for how many upsilon bound states you expect to see at the end of the day in your detector. So that's to say there is space for one to try to understand what is the microscopic dynamics that leads to these suppressions. And I'm just showing the upsilon, yes, and that's deliberate because I'm gonna, in the next few slides, discuss an effective field theory that's very good for upsilons, but not so good for charms. But yes, for charmonia, you have very similar plots as well. Though I have to say that because the mass of the charm quark is lower, the non-relativistic expansion that I'm going to discuss is well under worse control. So there are more puzzles in data in charmonia than in bohemia.
This is the same
This is
CMS.
This is from Alice. It's a
Yeah,
so it's different experiment at CERN. Both plots actually show the same data, and they're overlaid with different theory curves, both as a function of how central the collision is.
These are both Alice.
These are both Alice.
So you're not showing the consistency between Alice and CMS.
So if you fix your eye there,
Yeah, sort of.
yeah, they argue with each other about these things. And I'm not going to wade into that discussion. Okay, so now what's the program to try to understand how do we improve these descriptions, and well, rather, how do we hope to improve these descriptions? So let's just look at this system, this bound state system of two heavy quarks. There are many scales here in the problem. So you have the masses of the heavy quarks, which are comparatively heavy to lambda QCD. You have the typical size, which is order of a GeV, so larger, but be careful. Their binding energy, so the separation between the different states that you can have, is about 500 MeV, so definitely not very far away from lambda QCD. And then if you put this in a thermal background, as in a quark gluon plasma with a temperature of 200 MeV, which is reached routinely nowadays in heavy ion collisions, you see that you have essentially 4 scales that you have to think about. And then, but if you're interested only in things that happen over time scales that are comparable to the temperature, then you can zoom out. And if you look at the size of the system you form when you collide these things, so the width of the screen is would be about 5 Fermi here. The inverse temperature would be about 1 Fermi. And the takeaway from here is that the bound state of a BB bar pair looks small. So we're going to treat it as a point-like particle and build an EFT around that. The idea is that you have a hierarchy of scales between the mass, the typical size, which you can think of as the inverse momentum of these non-relativistic particles because they're heavy, and then that in turn is larger. Well, the mass scale is larger than the temperature. Okay, so there's a way to construct an EFT for this systematically. You would start from QCD, you'd go to integrate out what people would call hard degrees of freedom or high energy degrees of freedom. You'd arrive at non-relativistic QCD, and then you'd integrate out some more degrees of freedom and arrive at PNR QCD. I'm going to spare you all the details thereof. If you're really, really interested, you can look at these 25-year-old papers. So I'm just going to give you the final answer. What the zeroth order Lagrangian that you can write essentially for a point-like bound state system interacting with a high temperature QCD bath is made up of these 2 terms. There's the light QCD degrees of freedom, which is your usual Lagrangian. And then for the QQ bar pair, you essentially write, okay, I should draw this. How do I, is this the eraser? Okay. So essentially, if you imagine that this whole board is the size of the essentially around the size of a Fermi, then I'm gonna say for upsilons, I'm gonna say that this thing here is about 0.2 Fermi. I'm gonna divide my space into boxes essentially labeled by the coordinate x, and from here I'm going to have another coordinate r that describes what's happening at very short distance scales, so how the wave function of these heavy quarks will behave. So that's why there's an additional internal coordinate here, and then each of these boxes essentially you label by the coordinate x, which is the one that light quarks and gluons will feel in a just because you've integrated out essentially all of the hard modes of the theory. So you're only left with excitations that are relatively long wavelength, so they cannot look too closely, or they cannot resolve with too much detail what's happening in the octet and singlet bound states here. Of course, you have interactions. It's not like the medium doesn't interact with the QQ bar pair. But the interactions in the limit where the bound state is small, they're essentially, you can do a multiple expansion of the gauge field and get transitions between singlet and octet states by emitting or absorbing a gluon into the medium. And that way you can make the bound state get dissociated or recombinated. By the way, this is just the same as what you'd, intuitively, the same as what would happen in a hydrogen atom. You have the force carrier mediating a energy level transition. Okay, so that's it. The crucial point out of all of this is that this is an additional process that you have to consider in addition to screening. So in addition to whatever medium modification the interaction between these two heavy quarks gets from the medium, you also have to account for the possibility that a gluon from the medium can induce a transition between these two states. And if you want to then have a microscopic picture to compare with data, you have to do this. Of course, I'm not going to get all the way there in this talk. I'm going to show you what you have to do if you want, and that's essentially the research program I've pursued in my PhD. Okay, as a summary, the Lagrangian we're looking at, the system we're looking at, is made up of three components. A system, which is a QQ-bar pair, which can have energy levels, bound or unbound. These are encoded in the terms in the Lagrangian that I've singled out there. Then you have interactions, which are mediated by these multiple expansion-like terms. And then you have QCD that essentially is quark-gluon plasma that surrounds this. And how you treat this in practice is using open quantum systems. So since you're only going to measure properties of the QQ-bar pair, your observables, you're not going to measure the state of the quark-gluon plasma at the end. So you can trace that out when you calculate how occupied or depleted a given state is. So that's just to say that in practice what you want to do is to write down the evolution for the full density matrix and then trace out the QGP degrees of freedom and hopefully derive an evolution equation for Quarkonia in medium. So which leads me to what you have to do to set this up. So again, this is an old subject in the sense that Peskin and Bond studied it some decades ago. But what you want to do here, if the quark-gluon plasma itself is strongly coupled, which, by the way, I should emphasize, the only expansion I've done here so far is an expansion on the kinematics of the states. I have not said anything about whether the QGP is strongly or weakly coupled. So these diagrams that you'd write here in a weak coupling expansion, they are good for a weak coupled calculation, but they're not necessarily good for real-life quark-gluon plasma. So you want to define observables, or rather objects that you can compute at each order in the power counting of your effective theory, which are non-perturbative on the coupling. And these objects we called generalized Gluon distributions because of some analogy with Parton distribution functions that is not quite yet realized in terms of inferring them from data, but you'll see how this goes. So there are two, and I'll just show them to you and then explain them. So there are correlations of functions of electric fields stressed by Wilson lines. And instead of going through the details, just let me show you the intuitive picture of what they mean. On the left here, you start with a bound state, a color singlet state. So you have no operator insertions at early times here on this plot. Then at some point, there's an interaction that perturbatively controlled by the power counting of your effective theory, by which the state transitions to an octet. And then it's color charged, so an adjoint Wilson line appears. You cannot neglect any of those contributions because they're not suppressed by the power counting of your effective theory. And so you have to put them in. As a nice side product, they give you a gauge invariant observable that you can calculate in principle on the lattice. In practice, you have to deal with problems that I'll not go into today if you want to do that. But at the end of the day, essentially, if you look at this as an amplitude, what this is essentially the absolute value squared, which you have to write in terms of a correlation function. Same thing for recombination. So the process I just showed you was dissociation. Now you start with an unbound state. You have a color charged particle. So essentially, if you want to think about color flux lines, each quark has a line that couples to something in the environment, and at some point, an interaction makes them bind to each other, and then after that, at leading order in this effective theory, they don't interact with each other, and they just continue flying away. Good. So, in summary, these are the objects that you'd need to calculate at finite temperature, non-perturbatively in the coupling, and there are two of them, and there's one distinction between them in that the initial state if you started with a state that's in the color octet representation, then you need an adjoint Wilson line along imaginary time to prepare your state, just because the quark-gluon plasma will know that you have a color charge there. it is what it is. Then you can, after you do this, you can say, well, let's try to calculate this. Before going there, these processes are, of course, the time-reversed versions of each other. If you have an initial state that's bound, and then you go to unbound, you also must have the inverse process, and they have to be related if you want to reach any kind of equilibrium state at late times, which will not be realized in a heavy ion collision because there's too little time. But if you had a way to form quark-gluon plasma that lived forever, this would be highly relevant for consistency. And the practical consequence of this is that you can write everything up in terms of a spectral function, which is what I'll show plots now. Well, again, I'm getting ahead of myself. How do you use these things? Or rather, how people would use these things. If you stay in the mindset that quark-gluon plasma is weakly coupled, you can do some more approximations and derive a Boltzmann equation for how these bound states evolve over time. So you have a number density, which evolves according to a dissociation rate and a formation rate. And all you need to know from this slide is that the spectral function I showed you just before appears explicitly here as the quantity that determines how small or large these rates are. Then the first thing you do is to calculate this in perturbation theory, just to see what happens. And I'm gonna, even though the regime I care about really for heavy ion collision phenomenology is where the frequency of this correlator is close to the temperature, so very much at the middle of this plot where I have no resolution in this figure here, that's not where I trust perturbation theory. So let me just have a, just let me calculate this thing as a correlation function in QCD, show you the result in the regime where I more or less trust perturbation theory, and see what it does. And what you see is that this spectral function develops some asymmetry between positive and negative frequencies, which is puzzling. The reason why this happens is actually because in this system, essentially, from the point of view of the quark-gluon plasma, you're transitioning between two Hamiltonians, if you want. You have one Hamiltonian for one period of time where you don't have any color charge that's visible for the QGP degrees of freedom. And then at some point you transition to a state where you do have a point color charge sitting there. And then, well, the whole state of the theory, the whole state of your system is a color singlet, it's gauge invariant, so the quark-gluon plasma will know about it. And because of that, you have essentially two different time evolution operators that you have to deal with, and that ultimately leads to that feature of that spectral function being not symmetric. The reason why I emphasize this is because we also did an ADS-CFT calculation of an analog correlator, and n equals 4 super Young mills, large NC, strong coupling. And what you see in that calculation, surprisingly at first, but in hindsight not so much, is that this tendency of this asymmetry that's being generated at positive and negative frequencies. Here I've just normalized things so that all the curves agree on the right-hand side and see how. So I've essentially added extra factors of the coupling so that things get balanced. What you see is that the trend as you dial up the coupling from the weakly coupled QCD result goes in the direction of the strongly coupled n equals 4 super Young mills result. That's not to say that I would believe that this curve, this dashed curve here is what I should use for a real-world QCD, but it is to say that if there are any effects due to strongly coupled physics that I can see in this curve, I should assess whether they can be stronger or weaker than the effects that people have thought about in the weakly coupled picture that you can get from the weakly coupled results. And of course, it's a nice picture in the regime where I have perturbative control in QCD. If I zoom into the regime where I go to really low frequencies, you'll see that actually the trend goes the opposite way. So take that with a grain of salt, but still, in principle, you have to think about how would the transport equations for Quarkonia change if instead of using your weakly coupled assumptions, you go to stronger coupling. And for that, we're going to use the The n equals 4 Scheihing-Mills result is a playground. And if you go back to the transport equations, you'll see that if you just plug and play, you get trivial dynamics. And there's a deep reason behind this, or perhaps not too deep. It's because in all of these curves that I showed you in the first slides, where I showed you the theory descriptions compared to data, there are assumptions that if you look at from the modeling point of view, that if you just inspect them closely, you'll see that they're intrinsically weakly coupled assumptions. And in particular, all memory effects, all correlations of the quark-gluon plasma with itself are neglected. And if you have a strongly coupled system, well, you should care about those. So we did the calculation, and then we looked at what were people doing. 3? Okay. It's just half hour. So when we looked at what people were doing with, even from first principles effective field theory techniques, we found that there's more to be done from the phenomenology point of view for the transport descriptions that people are using, essentially. So what we did to begin with, just to show that even if you don't make all the assumptions that other people do, if you just start from open quantum systems and do an expansion in the power counting parameter of the effective theory, so temperature over the inverse size of the Quarkonium bound states, you can get an expression that, by just expanding the time evolution operators here. And while we have not looked into this in as much detail as we will in the coming months, we can still get a result. We can get what the regeneration probability is, say for the upsilon 1s state, essentially having the Schrodinger equation coupled to a quantum field theory, which is filled with quark-gluon plasma, using the correlator from holography, evolved over time with a semi-realistic temperature profile of the QGP for about 10 Fermi, ending at 155 MeV. And you see that physically the plot looks sensible. You have some non-zero regeneration probability that I have not yet compared with data, so don't push me on that, which with peaks right around the sizes that you would assign to, say, the upsilon 1s state, and then this kind of wants to be in medium 2s resonance. Each point is a different realization of this of the formula that I had back here, initializing the heavy quarks at a different distance from each other, and so you just see what's the probability. As you pull them further apart, they're less and less likely to recombine, essentially. Okay, so that's it. So I think I went. Okay, so what we have been doing here is to try to formulate from effective field theory, and succeeded, what are the objects that you would have to calculate non-perturbatively on the coupling constant to get to describe from first principles dissociation and recombination of quarkonium in medium. And here, well, you can do calculations at weak coupling in QCD just by hand. If you want to do strong coupling, you have to do lattice, and we have been thinking about how to essentially provide some aid to the analytic continuation that you have to go through to get from imaginary time to real time, which is a problem. But at strong coupling, if you're just willing to look at qualitative features, you can use holography and see what things look like, and which is what we did. Now the next steps are less theory inclined, they're more now phenomenology inclined, just because we have a set of results that we now want to use and compare with data and see if we can beat all of those curves that I showed you in the first few slides. So thank you very much for your attention, and I hope you have a great evening. Questions? It's almost 6 p.m.
So you said the problem with lattice data is mainly the Euclideans, so the big rotation, or is there? I mean, yes. You also, I think it might be difficult to go to the continuum.
So there should be an expert here in the audience. There's an expert back there, Patrick, with whom you can talk later on. Yeah, I'm not so worried actually about the continuum limit. I'm more worried about the analytic continuation, because if you look at, because what you do is calculate the correlator in imaginary time, and then decompose that in Matsubara frequencies. So, and then you'll have a finite number of them. And the number of those points that are actually sensitive to finite temperature effects are 3, 4. So you have to do an analytic continuation to a continuum function, to a continuous function, where all of the information you really care about is encoded in a small set of points. So the problem there is how you use everything you have to do the Wick rotation. People are thinking about it. Patrick back there is thinking about it. So
the problem is like extremely opposed. So like given as Bruno was saying, like given a set of Euclidean correlation data, like there are an infinite number of spectral functions, reconstructions you can basically get from doing that Wick rotation, since you only have it at some very small number of points. So you can actually use the analytic property of the function, of the whole analytic, or the whole structure, to constrain what type of analytic continuations you can get. But it's a difficult problem, and we're
Is it the classical inversion problem?
Yeah, exactly.
So in the beginning, you showed theory versus experiment,
mm-hmm.
and then you presented a better theory, right?
Well,
You
a
hope.
theory that has every hope to be better.
Yeah, that was that. There's no theory there. So how does it what you talked about differ from these things?
So the one that's easiest to compare with, I would say, is the coupled Boltzmann equations here, which use which actually use the Boltzmann equation I showed below, but with a correlator evaluated at leading order in the coupling, so a weak coupling. So before essentially we realized that we actually need to resum everything with Wilson lines to formulate that. So my first step would be so it should be at least better than this, for sure. And then we have and then we have to play around with essentially what we can play around with and see whether different Quarkonium states feel a different coupling constant, and it's because they're sensitive to a different scale. So there's a lot of things that you have to look into and really make sure that you're doing things correctly. But by the way, I in these figures I've shown you here, you can ask how am I treating the scale, and to produce these plots of these distributions, I'm using the running of the coupling constant of QCD up to 2 loops to fix the scale. So we believe we have enough knowledge of in the weakly coupled side and the strongly coupled side to at least have a decent interpolation.
Okay, there was one other question about the theory and your theory.
Oh,
yeah.
and which slide? Okay.
No, the actual comparison with data.
Okay.
So, yeah. So the error bars are pretty big, and you'd like to do better, right?
Yes.
So what?
I'd like to do
how
better.
How do you?
I'd like to do
How
better.
do you establish error bar?
Good. There are several contributions. So before I forget, I not only want to do better, I want to do better and provide a microscopic description of what's happening here. Because at some point here, you
want to do better, you presumably also want to predict something that hasn't been measured.
Yeah, I'm hoping that, well, I'm showing you plots that people typically show around, but if I talk to, say, Yanji Li, I know he has data for which he's puzzled about, and he'd like me to, explain eventually. Now, about estimating the error bar, so there's So, well, the first thing, the biggest contribution I would say comes from the power counting of the EFT. And for that, you can estimate that by looking at the, how much smaller the contributions in this expansion on R times T essentially are, compared one term with the next leading order term. There are error bars as well that would be statistical in nature of how the evolution of the quark-gluon plasma happens, because you can simulate this in theory for one temperature profile over time, but when you compare with data, it's an average of all things. So you have to also do that average, which also will at least give you the boxes here, which are the systematics. There's plenty to think about, but it's an interesting problem. I hope I convinced you of that at least.
And you think there'll be other questions to charmonium as well, or that's
Oh.
too light?
For this, the problem with charmonia is that with botomonia, you're fairly sure that the BB bar pair that you see as a bound state was produced together from the same hard scattering process. For charmonia, they're light enough that they can get kicks from the medium that make them recombine in an uncorrelated way. And so you have to go beyond this Schrodinger equation picture where I only have two heavy particles that bind to each other, but I have to essentially follow the, say, 30 or 50 heavy quarks that are produced, which is a much harder problem, just computationally. But people try this. I mean, there's a similar curve with coupled Boltzmann equations for J psi that the people before me have done. Okay. I think it's a good time for dinner, unless there are more questions.
I agree.